is we talk about the point, and then we can talk about whether the point is defined, whether the point limit exists, whether the point is continuous, or whether the point is differentiable. That's the 4 things we can discuss for a point. We have go through the first 2. So for defined, I said when I have x equals to a, you can work out the y value for that x, then it is defined at that point. So this is not open circle, or there's no gap in between that point. The next one is the limit. Okay, limit is when you approach from the left-hand side to that point, and when you approach from the right-hand side to that point, you approaching to the same y value, then we said the limit exists. Well, I go through the method is y can draw a vertical line there, and then at the point we're trying to investigate, and then you can think about 2 people walking along the path from left-hand side and right-hand side. When they stop in front of the wall, are they approximately at the same level? Are they trying to approach to the same point? If they're approaching to the same point, then we said limit exists. When they're not approaching to the same point, or think about this diagram, they're not even approaching anything, then the limit does not exist. Okay, so just keep forever going, like you will never hit the wall. So you will have no limit for this graph. Well, for this one, yes, we're approaching to the same point, then we have the limit. For the third one, left-hand side, right-hand side, we're trying to approach into different points at different levels, then we don't have the limit. And then for the last one, even though it's an open circle at x equals to 0, but when I walk along the path, I'm still approaching to that open circle. So it doesn't matter if it's defined or not, the limit can exist anyway. So we have like something where at x equals to 1, even though it's open circle or closed circle, if the function looks like that, then limit will exist for both graphs. But when limit will not exist, when there's a vertical jump or horizontal jump, like when the graph is not connected, like we approaching to different points. Therefore, we said the limit does not exist for the other 2 graphs. And now today is, well, you know you won't really sketching all the time when you're trying to find limit. Like give you a function, ask you to find limit, you're not going to sketch it every time. So what you will do is, that's what we learn to how to find limit. Okay, how to find limit. First of all, let's have a look at some theorem. For 4 of that, well, 3 of them is useless. So 2, 3, 4, they are useless, very useless, because you will never use it in high school level. Well, in uni, yes, you use them, but in high school level, we don't care about that. So the only important one is Theorem One. Okay, so what that said is limit for a constant value, if y equals to c, for a constant value c, like, so the function is a horizontal line. Okay, it's a horizontal line. It's same as this diagram here. It's just y equals to c, it's a horizontal line. When we have that case, the limit of anything will be the constant itself. So for example, limit x approaching to -1 of 3, that is still 3. Well, if I change -1 to 2, it is still 3. I change that to 100, it's still 3. So the limit to a constant, limit of any number of a constant function is still the constant itself. Okay, still the function, like the constant, the function is the constant. So it's the constant itself. Okay, so that's the only useful one. Ask you another thing. See, it's the extension for this one. Okay, it's the extension for this one. Well, we know lim x approaching to 1, like, or -1 of 3, that equals to 3. How about lim x approaching to 0 of 3, 3 plus h? No, that's 1. 3 plus h. What's the limit for that? What is your variable? X or h? Your x is the variable, so it's varying your x approaching to 1. So therefore your h will be a constant. Well, it's a number. Like, I don't know what is it, but it's a number. So the limit of this function is 3 plus h. It's still the same case as x approaching to something over a constant. Because in your function, there's no x, there's no variable. So it's not varying. This function is not varying when x varies. So it's still a horizontal line. Doesn't matter what is the h value. So h is just a number. So it's not varying when the x is varying. So it still belongs to the theorem number 1 because we don't have the variable, then we treat everything as a constant. Does that make sense? When we don't contain the constant, we don't contain the variable, we treat everything as a constant. Okay, we treat everything as a constant. What's the other two theorems talk about? Is just when we find the limit of a of a function minus or plus another function. It's the same, find the limit of one function plus minus of the limit of a, find another function. So just separate that. For example, this one I can write limit x approaching to 1 of x cubed plus limit x approaching 1 of 2x. But what's the use of it? Like, doesn't really matter. Like when I separate it, it just takes extra step. I can directly evaluate when the function is x cubed plus 2x. So I don't need this. It's quite useless. But like there's some rule like this. You can separate them and then find the limit separately and then plus them or minus them. So same as the next two. When we times two functions, we can find the limit separately and then times the result together. When we divide two functions, we can find the limit separately and when we divide them. That's it. Okay, that's it. That's all the other three theorems talk about. Okay. That's not important. What I want to talk about here is how do we evaluate like a real limit? For example, like you can see there are all functions and the limit of x is limited to different values. So what I can do, we basically follow two rules. First, can I substitute that x value into the function? You know, like all the limit value is actually when x equals to that and the y value, right? Like that's actually the limit. Like this y value, this point, even though I'm trying to say lim x approaching to 0, but it's still the y value at that point. The limit is the y value at that point. The limit is the y value at that point, but it's an open circle. But it's still the limit, like the y value of that open circle, the coordinates of that open circle. So what all I want to do is, can I find the y value when x equals to that? If you can find that, then the limit value is just that y value. So can you substitute x equals to that number into the function? If you can substitute, we directly substitute. The value you get out will be the limit value. But there are some cases you cannot substitute. For example, f. If I want to sub 0 into the function, what's the problem? Yeah, denominator is 0. So when we cannot substitute the function, cannot substitute the x value into the function, what we need to do is we need to simplify the function first, factorize, simplify, and then see if you can substitute. Okay, after you reduce something, we get rid of something, can we substitute? Until we make the form, all right, like I can substitute, then we substitute, then the y value we work out is the limit value. So we basically follow these two rules. Well, first one is easy. What's the limit value of that? 10. Limit of a constant is still the constant itself. Doesn't matter limit to which x value. So it's always that constant itself. It's a horizontal line. Okay, can I substitute here? Yes. So if we can substitute, we can get rid of the limit. Okay, we don't have the limit. We do substitution. That's 2 times 5. And that's a 10. Okay, the limit of that is 10. We just substitute x equals to 0 into that function. Can I substitute this? Yes. Then we 5 minus 7 times negative 2 over minus 2 minus 2. So that's a 19 over negative 4. Okay, the first three is easy. I can substitute or it's just a constant. But let's have a look at the next one. Can I substitute this one? No, denominator is not good. What I can do to this function? Simplifies. So when we simplify, we haven't substitute. We need to keep the lim value. So what all you need to do is with that. So we can simplify that as a 2x plus 3 over 5. Okay, divide x plus 3 on top and bottom. Can I substitute now? Is that possible to substitute? Yes, I sub negative 3 in, that's just a 0. But it's not that easy. Like, let's consider if I have a function y equals to 2x plus 3 cubed, 5x plus 3. Well, I can simplify it. That becomes 2 over 5x plus 3. Can you tell me what's the second function, like this one? What's the name of that function? What type of function is that? Start with L? Linear. Okay, it's a linear. So if that's a linear, let's sketch this linear. Okay, let's sketch this linear. So I'll use the space here. Okay, we have this line here. Well, this point is 0, 6 on 5. This point here will be minus 3, 0. Okay, no problem for that. My question is, why sketch this one? Is that exactly the same as the next, like this line? Is that exactly the same or not? Like, I simplify this thing into this linear function and I sketch this linear function. Are they equivalent? Are they the same thing? If I want to sketch, say, function A and sketch function B, do they have exactly the same graph? Yes or no? Who think yes? Well, that's fine, like just yes, okay? And the rest of you think no, okay? If you think about no, why not? But any of you think no can give me a reason, like why not the same? I give you a hint. Think about the implied domain for both functions. What's the implied domain for the first one? What's the implied domain? Is that R? Negative 3, right? So the implied domain is x belongs to R except negative 3. Your x can't be negative 3 because denominator can't be 0. What's the implied domain for the next one? The B. R. Okay, x belongs to R for the next one. So you can see they're not the same. Well, the rule is the same, but the only thing is, well, when I simplify A, I can have B. The rule will be kind of the same. But the difference is I have different implied domain for A. Okay, I can have anything else except negative 3. So at negative 3, I should have an open circle. That's what the function A looks like. Function A is a linear, but there's restrictions to make it become a linear. If x is negative 3, the function will not exist. At x equals to negative 3 is not defined. So therefore, we don't have x equals to negative 3. Therefore, it's an open circle at x equals to negative 3. So that's the difference between the first rule and the second rule. Okay, that's the difference between the first rule and second rule. your implied domain is found by the original function, not by the simplified function. So every time you're trying to work implied domain, you need to look at the most original function, not the simplified one. Because the simplified one will get rid of a lot of things and you can't see what the original domain should be. So to make this function a to be true, your x can't be -3. That is your implied domain. If x is not -3, then I can divide x plus 3 on top and bottom. If x is -3, how I can divide 0 on both top and bottom? So I can't do that. So therefore, we will have an open circle. This is function a. Okay, this is function a, what that looks like. So the limit still exists. That's why the limit still exists. I just get rid of the thing and I want to see on the function b what's the y value. Even though that's an open circle, that's the same as a closed circle to find limit. So it doesn't matter if it's an open circle or closed circle, I can find limit anyway. So that's why I can do simplifications in the second step and then do substitution in the third step. Alright, so that's the difference. Well, it's easy to find the value, but it's important to understand why we're doing like this. Okay, why the graph is different. Okay, for E. Okay, for E. Can I substitute? No. What I can do to that? Factorize. So what's the factorize on top? Minus 3 minus 3 minus 2, right? That's give you a 6 and a minus 5. And I'll divide by x minus 2. So what I can do is I can simplify those two from top and bottom. And then I can substitute now. The substitute value is -1. Okay, the substitute value is -1. What's the domain for this one? Except 2. Okay, except 2. So it will be an open circle here. Okay, that's an open circle, 2, -1. Okay, 2, -1. So open circle here. Yeah, that's how the graph looks like. Okay, for the last one, I can't substitute. What I can do? Expand, simplify, we can do that. Any other way we can factorize directly? Difference of perfect square, I can do that as well. So lim x approaching to 0, I can go 3 plus 2x plus 3. 3 plus 2x minus 3. Divide by 2x. That's lim. Well, when you not substitute yet, so you will keep the lim. Okay, until you put the x value in, then you get rid of the lim. So 2x plus 6 times with 2x and divide with 2x. The 2x can be cancelled. What I will have is a 6. Okay, a 6. But we know 0 can't be our domain, so we have an open circle here. That point is 0, 6. And I can have closed circle here, -3, 0. That will be the graph. Okay, that will be the graph. Okay, that's the way how we evaluate limit. Okay, how we evaluate limit before we sketching the graph. Okay, now we're going to talk about the next definition. The next definition is important, and there's 3 things to prove it is the continuous. Okay, let's talk about the continuity, whether a point is continuous or not. We talk about the point, whether a point is continuous or not. If you look at the graph, it's very, very easy. You just need to think about one thing from the graph, okay, from the graph. The thing is that the graph connected at that point? Is that point joined at that point? For example, for the 3 graph below here, I will talk about the continuity at x equals to 0. Well, if you can see here, well, it's not that obvious, but here's an open circle at x equals to 0. There's an open circle up here, and there's a closed circle at the bottom. And for the next one is an open circle here, but it's a closed dot on top. Okay, let's jump up. So my question is x equals to 0 continuous or not for these 3 graphs? The answer is no, like it's not continuous, like it's not joined together, it's not connected at that point. Well, first one, like we don't have a value, like it's stopped, like it's an open circle, it's not connected at that point. For the next one, well, a vertical jump also is not connected. For the third one, well, we do have a value, but the point is not connected, it's not hand by hand like this, okay? So it's not connected together. So these 3 graphs are not continuous at x equals to 0. It's continuous at all the other points. Okay, it's continuous at all the other points, but not at x equals to 0. Because all the other point is joined together. Okay, is joined together, but not x equals to 0. But the thing is, you won't always have the graph. And well, even though you have the graph, they may ask you to prove why it's not continuous. What's the theory you use to show it is continuous? Okay, you need to give me theories why it is continuous or why not is continuous. So the 3 things, okay, 1, 2, 3 is they need to satisfy at the same time, okay? Not 1 or 2 or 3. So it's 1 and 2 and 3. It needs to satisfy 3 things. The first thing is the point must be defined at that value. The second thing is the limit must exist at that point. The third thing is the limit value must be the same as the defined value. So the y value must equals to the limit value. Okay, the y value must equals to the limit value. So if you go back to the front page, what I ask you to write, okay, this. Okay, I write arrows in the right-hand side direction, which means the defined and limit will decide continuity. Continuity will decide differentiability. So if it's not defined or not limit exists, we won't talk about continuity. It's already a no. Okay, if those two not satisfied, it's already a no. But if it's defined, if limit exists, we still need a third condition to test is continuous or not. So if don't satisfy the left-hand side, right-hand side is definitely a no. But even though we satisfy the left-hand side, the right-hand side needs one more condition to talk about to make it true. So in the same idea, if the point is not continuous, we don't talk about the differentiability. But anyway, we haven't talked about differentiable yet. But just let you know why we write this in this order. Because if the left-hand side one is not true, then the right-hand side one can't be true. Even though the left-hand side one is true, we need one more condition to test about the right-hand side. So that's the relationship between them. If it's not defined or not limit exists, it can't be continuous. If it's not continuous, then it's not differentiable. So we go back to what we have here. Okay, remember requirement 1, 2, 3. First one defined, second one limit exists, third one the limit and the defined value must be the same. Let's have a look at the first one. Is it defined at that point? F0 defined or not? No. Okay, so it's not continuous. So not satisfy the first one. F0 is not defined. Okay, F0 is not defined. Therefore, not continuous at x equals to 0. Okay, for the next one, is it defined? Is it defined? Yes, defined. So F0 equals to what? 0. It is defined. Okay, a tick for the first one. Okay, is it limit exist? Is it limit exist or not? No. Okay, so how we talk about limit does not exist. What we need to write is limit x from the left-hand side of 0 of that function. We have 0. We limit approaching to 0. We'll limit x approaching to 0 from the positive side. We approaching to 1. Okay. Limit x0 negative of fx is not equal to limit x0 right-hand side of fx. So limit of x approaching to 0 of fx does not exist. Okay, the limit does not exist. So, not continuous. At x equals to 0. So it's not continuous at x equals to 0. Okay, so it doesn't satisfy the limit, so it can't be continuous. Well, for the third one, you may just a little bit confused. Why the defined value can be different from the limit value? Okay, so why the defined value can be different from the continuous limit value? So if we have a look at this question, is it defined first? Yes, what f0 equals to? That's 1, that's 2, that's 3, 4, 5. 3. Okay, f0 equals to 3. The pink point is up, okay? So equals to 3. It's a jump. Can I see there's a slight dot on your diagram? So that's f0 equals to 3. Okay, limit x approaching to 0 equals to what? One. Okay, if you go approaching the wall 0, you're actually approaching to this point. It's more closer and closer and closer to 1. Okay, you try to reach level 1. Okay, you can't realize the sudden change. Like limit is just generally go up, up, and down, or down, and then we work out that's approaching level 1. So the limit actually equals to 1 in this case. It's not approaching 3. Okay, see, when x equals to, say, that's 1, that's about 1. Then when you reduce 1, the value reduced maybe to 1.5, and then keep reduce 1.4, 1.2, and then 1.0, 1.001, 1.0001. So it's actually, even though I never reached that point, like limit is a reaching value. So when all the point decreasing, it's decreasing to 1. It's regardless what you have for your original function. It's not limit. It depends on the trend of the whole function. When you get close to that point, what's the value approaching to? Do you get the idea? Okay, so even though we have a point 3 there, but the limit will never reach that point, because if you walk along the path, you are like reducing to or increasing to level 1. So the limit is 1. Therefore, you can see f0 is not equals to limit x approaching to 0 of fx. Okay, they are not the same. So x equals to 0 is not continuous. Okay, x equals to 0 is not continuous. Okay, one last thing we'll do. Okay, first of all, can you sketch both hybrid functions according to the domain, please? Okay, sketch both hybrid functions according to the domain. Make sure you label all the endpoints, correct open circle or closed circle, all the x, y intercepts. Okay, if you finish, you can have a look at the graph I have. Okay, when you finish sketching, you can think about the continuity for the whole function. Well, what I mean the whole function means like all the single point. Is there any point which is not continuous? Or say for the entire function is all continuous? Okay, so I want you to think about the continuity for all the points. Okay, for the first, well, I should have graph like the first part is a linear 0 to 2, a decreasing 1 minus x plus 2 is like 0 to 2, 0, like it's that part. So it's a linear. So for the next one is a downwards quadratic. But I start from 2. When I start 2 in, I have 0, which is just the x-intercept. But it's an open circle. Anyway, it's overlap with the closed circle, so that becomes a closed circle, like they join together. And then like it's a decreasing function, and then reach 6, negative 32. When I sub 6 in is 4 minus 36, that's a negative 32, okay? So we have this function here. Do you think the whole function is continuous, or is there any point which is not continuous? It's continuous everywhere, right? It's continuous everywhere. What we will think about for this question is the connection point. Where's the point trying to join the two functions together? We have a linear function, we have a quadratic function. When x equals to 2, they are trying to join it, right? One is open circle, one is closed circle like this. Well, if they overlap each other, which means this point is successfully joined together, they connected. Well, if one x is here and the other value is here, then it's a vertical jump between the curve, or even like this, which means it's not connected, it's not continuous at that point. For the rest of the point, well, you know for a linear function, there's no holes, there's no jump, like it is a continuous function, right, for a linear. For quadratic, it's the same. There's nowhere like stop or break, like it will be continuous. So the only point might have problem is when they're trying to join each other. Okay, when they're trying to connect each other. So when I sub x equals to 2 into the first function, I got 0. When I sub 2 into the second function, I got a 0 as well, even though that's an open circle. But they join together, right? They join together. So that's why we have continuous function here. Is continuous over the domain 0 to 6. Okay, it is continuous over the domain everywhere 0 to 6. It is continuous at x equals to 2. So everywhere is continuous. 2 is the point I need to investigate, because that's the only point it might have problem. And now I can see for the first function I got 2, 0. For the second function I got 2, 0 as well. So the point is joined together. They are actually the same point. So it is joined. So it is continuous at x equals to 2. But for this function, it's asked you to talk about the continuity of the function. So it is continuous everywhere. Okay, it is continuous everywhere from 0 to 6. Well, for the next one is a linear join a quadratic as well. And the point they're trying to join each other is at x equals to 3. Well, it can be a join point. It can be a jump point. So for this one, without sketching, I will have when x equals to 3, 2x equals to 6, x squared minus 9 equals to 0. So I have 2 points, 3, 6 and 3, 0. 3, 6 is an closed circle. 3, 0 is an open circle. you can see they're not joined together. Okay, it's a jump. It's a jump. They're not joining each other. And also that has been shown on the graph. At x equals to 3, we have some graph like this. Okay, we have some graph like this. So we'll say the function is not continuous at x equals to 3. Okay, the function is not continuous at x equals to 3. Okay, so for this type of function, like when you talk about the continuity for a hybrid function, the only point you need to worry about is the connecting point. It's like the point they're trying to join each other, they're trying to connect each other. So you don't really need to sketch the graph. You just need to find the value at the same point at different function, like at function 1, function 2. Then you compare the y value. If they are not the same, then you will say it's not continuous at that point. If they are the same, you will say that point is continuous, as well as all the other points, right? Like the other part is no problem. Like on one function, every point is continuous. Every point is continuous. If there's no asymptotes, no like open circle, it will be continuous. Okay, so this is the continuity. So you need to know two things from continuity. First, you need to be able to tell whether the function is continuous or not. Second, you need to use the rule to prove whether it's continuous or not. You need to label why it is continuous, especially why it's not continuous, which one it fails. Okay, the first one define, or the second one limit exists, or the third one limit and exists is not the same value. Say for this one, it's not continuous because the limit is not the same. Okay, limit from the right hand side is 6, from the left hand side is 3, so it's 0. So the limit is not the same. Therefore, we don't have continuity at that point. Any other questions for today? Well, I think it's one exercise, like what we do in these two lessons, one exercise for 17F. Okay, it's a lot of definitions, 3 definitions in this exercise, which is very important. Next lesson, we'll talk about derivatives. Okay, we'll talk about derivatives, like it's the gradient of the tangent. So that's what we do for tomorrow.